Alejandro Mendez, and in this video poster, I'll give you a peek at recent work where we implemented machine learning techniques on the International Atomic Energy Agency Stopping Power database. This was a collaborative effort between Felipe Vibor-Hayek, Dario Mitnick, and Claudio Montanari. When ions hit matter, they are decelerated due to interactions with the matter's nuclei and electrons. This deceleration force gives the average energy loss per unit length, also called stopping power. We can decompose the energy loss contributions into two distinctive parts. We will focus only on the electronic contribution, which features the characteristic Bragg peak. This particular behavior differs from the way other projectiles lose energy, for example, X-ray or electrons. Understanding this phenomenon became of great interest recently due to its application, particularly in proton therapy. The IAEA Stopping Power database is the most extensive stopping power data collection. This database was kickstarted in the 90s by Helmut Polt and is now under Claudio Montanari's scientific supervision. The database's latest update consists of over 60,000 experimental measurements. This qualitative description arranges the data by ions with light blue bubbles, and inside them the small circles refer to the targets. At first glance, we can see that hydrogen and helium are two of the most studied ions, while boron on silicon dioxide is one of the most studied systems. Here's an example of this data. For hydrogen and gold, we can find 80 years of experimental measurements spread across the energy range. We clearly see there is quite a spread in stopping maxima. This behavior is compatible with other metallic targets such as silver and aluminum. Our work aims to model this phenomenon using a neural network and the experimental measurements. We want to understand and predict the electronic stopping power of ions first in atomic targets. However, we cannot use the raw data to train the neural network. We first need to clean it. For this, we implemented a density-based clustering model, which considers a minimum number of points in a neighboring radius around the data. This technique finds outliers, called noise points, and allows clusters of many shapes and sizes. We use DVScan algorithm, which requires only two input parameters, and it classifies points as belonging to a cluster or a noise point. For hydrogen and gold, the experimental measurements are organized into various clusters with minimal values marked as outliers. However, many values are considered noise for hydrogen and copper, with only a few marked as belonging to clusters. We cannot be expected to inspect the 706 collisional system under consideration, so we had to devise a density-based cleaning algorithm of our own. I will not go into detail about it, but you can check it out on our latest archive. Our cleaning algorithm allows us to keep all the data points with meaningful information, discarding noise values. Then the remaining data was divided into training and test sets. At the same time, the training was split into two. One part is used to train the neural network, while the other is used to validate or evaluate the training. This training was performed one experimental value at a time. That means that we use one input energy value and we make it correspond to one stopping power output value. Details about neural network architecture can be found also in our manuscript. Other input features were analyzed. First, we included the charge and mass of the projectile and target along with the energy value. Then we improved the model by linearizing the energy. We also included the first ionization energy of the target, and the model was improved even further. However, combinations of other ionization energies and electronegativities were unsuccessful. The neural network was tested by checking its prediction for the test set. As you can see, the predicted values are remarkable. A closer inspection of the results shows our mean predictions to be within 5%. An excellent example of our neural network's capability can be seen in the case of oxygen on silver. The DVScan tags most points as outliers, but our algorithm decides to keep the majority of them. The ESPNN predicted values follows the intermediate and high energy range experimental data, but even though it had no information in the low energy region, the model accurately predicts the stopping power values. Our current open source model is freely available in a GitHub repository and PyPy. The code is easy to install and user-friendly. You can install it via pip, and you'll only need to provide the collisional system to get the stopping power results in a graph or an output file. It can also be used remotely via Google Cloud. There's still plenty to work ahead, but we are excited to get feedback from the community to improve our models and layout, so feel free to reach out. Many thanks for watching, and I'll see you the next time.